Right, I'm assuming you've had enough time to read the problem. So let's go directly to the solution. Okay, what we're doing is, there is a problem. Is a mathematical programming formulation. Okay, what are the three components of a formulation like this? Same question as always. Same answer as always as well. What are they? Come on. Yes. So I'd rather start with something else. Okay, the thing without which you can't write your objective is the decision variables. Okay, if you have your decision variables, then you can write the objective. It's not my thing, is it? You can write the objective, and you can write the restraints as well. So in this question, or in this example, just constraints, but there's nothing there yet. Let's read the example. We have a company that produces two kinds of vehicles, stacker trucks and cherry picker. What is a stacker truck? I've got a picture. Something like this. And what is a cherry picker? It's something like this. Okay, so it's a manufacturer of these kind of vehicles. And let's go back. And they manufacture nothing else. And then they have some things there. Okay. There are slightly odd constraints. Well, we're not doing the constraints yet. What are we doing? We're doing the decision variables. What are the decision variables in a situation like this? So remember, this is very similar to the chess set problem. Typically, when you have a problem where there's some production and there are some resources, and it's a simple question like this, your decision variables are usually one for each type of product that there is. Okay. In this case, there is one for how many stacker trucks to produce and one for how many cherry pickers to produce. What do I call them? I don't care. So I can call them S and C, for example. So S is the number of stacker trucks produced, I think I should say per month, because all the other numbers that appear in the text are per month. And then C is the same. So it's the number of cherry pickers produced per month. Is that surprising? No. Okay, what is the objective? Well, you have to guess, because it doesn't say explicitly what the objective should be. So, what do you guess the objective should be? Oh. Okay, what's the formula for the profit? It's too simple. Yeah. Okay, stop asking if it's too simple. Well, 5,000 times S plus 7,000 times C, because each stacker truck gives you £5,000 profit, and each cherry picker gives you £7,000 profit. So you're producing S of the one and C of the other. This is what your profit is going to be. Okay. Is that the objective? Why not? No, that's what every objective function is. Okay, so you're doing linear programming, you want to, once you know, the decision variables are the unknowns. Those are the things that you don't know when you're writing your formulation. Okay? So then, I lost the point again. But then once you know them, everything is easy. But, yeah. So the point is, yeah, it's a function of the number of stacker trucks and cherry pickers to produce. And that's the objective function. But there's one bit of information missing there, and that is what you should do with the profit. Yes, yes, you should probably maximize it. That is indeed true. So, right, when you the objective consists of two things: the objective function, which is this function, and the word maximize or the word minimize. That's what the objective is. Was you want to find the optimum, but the optimum can be either the maximum or the minimum, depending on what problem you have. And that's the objective. That's simple. Now let's have a quick look at the constraints. So when you read this, I don't know if it's easily readable, but what it says is that they can build up to 100 stacker trucks or up to 80 cherry pickers, or any linear combination of these. You guess what constraint it is. Challenging. It's not as easy as the chess, but it's almost as easy as the chess. And George is creating an answer. You got an answer? Okay, give me one.
Stackers.
Well, that is true, but okay, that is true. Next.
X1 is less than stackers. So
I don't know why. Okay.
it says the stackers are about twice as many. So that's the
Where's that? Oh, that's the second constraint. I'm still after the first thing. So the first bit, which says that you can build up to 100 stacker trucks or 80 cherry pickers, but you can't make both. Okay, so if you just put one constraint that says no more than 100 stacker trucks, and another constraint that says no more than 80 cherry pickers, and these two constraints still don't prevent you from creating 100 of the one and 80 of the other. So what this sentence says is you can either do 100 of stackers or 80 cherry pickers, but not both. Or you could take what we call the linear combination of these. So you could take, for example, 50 stacker trucks and 40 cherry pickers. If you spend half the time on stacker trucks and half the time on cherry pickers, you make 50 cherry pickers. Or if you spend 10% of time on one, then you get 10 and 70. Any combination like this is okay. You can't do both. So one way to write this constraint is perhaps quite tricky the first time you see it. So you divide S by 100 and C by 80, this can't be more than 1. This is the body shop constraint. Do you believe me? Okay. This is exactly what you want. Think about it. Okay, then you've got the assembly shop. You can make most 60 cherry pickers. Or you can make twice as many stacker trucks. Or it can make a linear combination of these. So if you put S divided by 2, yeah, and that's the constraint. Okay, it's perhaps a bit cool. So if you only build cherry pickers, you can make up to 60. Okay? If you only build stacker trucks, then you can make double the number. So you can put 120 there. And again, you can split the time in that department between stacker trucks and the cherry pickers. So you can get everything. Some people do 60 of these and 30 of these. Make sense? Well, that's what it is. Then the paint shop constraint is kind of easy compared to these two, because for every stacker truck you need 1.3 hours. So in all you need 1.3 S hours. And for cherry pickers you need 0.9 C hours. And the total number of hours you have is 117. And that's the hours for the paint shop. Okay. And then there's the bank. And the bank wants at least 80 vehicles produced every month, which you can achieve by saying that the total number of vehicles produced is greater than or equal to 80. Any other constraints? Non-negativity? Pardon? No. Well, they're above 80 in total, which could mean that you could do, that makes sense, but suppose you could do something like put S to 100 and C to minus 20, and you'd still get feasible solution. It satisfies all these four constraints. Yeah. Yes. We're not there yet. Have you solved it already? Okay. Okay. We'll get there. We'll get there at some point. I think we're too way ahead now. And back to non-negativity. Yes, you have to put the non-negativity there. They both have to be greater than or equal to 0. So I'll say that again. So if you don't have this, and you could, I think if you do S equal to 100 and C equal to minus 20, then you still get. Maybe you don't get this, but something like that. Is that right? Okay. So you could get negative values, and you can't get negative values in the interpretation, obviously, because you can't build negative numbers of cherry. So this finishes the formulation, and solving it using Mosul is a homework problem. So I won't tell you the answer yet. Okay, what would you want the question? What would you want the answer to be integer? Well, you don't need the answer to be integer because you're thinking that your business is going on forever. So if it's telling you to build a third of a cherry picker, for example, then just start working on it in that particular month and finish it later. And then in 3 months' time, you'll have an extra cherry picker rather than having to make an integer number of cherry pickers. If that makes sense. I think it doesn't. Okay, any questions? Any other questions about this formulation? Well, then let's do another one. Okay, you don't see the table. Sorry, you can see the text there, and the table there, and the picture there as well. Okay, so what's going on here? Nobody really knows because people usually don't know. This matter. Going on here is you've got a factory. This factory buys Gummiberry juice. So Gummiberry juice comes into the factory, flows into this pipe, and Gummiberry juice is used by two machines. For the purposes of this example, we call the machines A and B. Each of these machines processes Gummiberry juice. Flowing into it. Machine A produces some of gummy ball. That red ball where it's coming. And it also produces some of intermediate thickened juice. Intermediate thickened juice is something you can't sell, but you can use it in machine C, cheese, gummy cola, and gummy ball. And the last machine B takes Gummiberry juice and produces some of the thickened juice. That's a sketch of the situation. That's there. Now there are some numbers that are given in this table. So these numbers are given tons of input into the machine. Okay? So whenever you pour a ton of Gummiberry juice into machine A, it costs you £35 to run it at that time. Okay? That's the cost. And for each ton that you pour into that machine, what you get out is 0.3 tons of wool and 0.3 tons of juice. This is what you do. Then you get 0.4 tons of waste, that's not part of this problem. Then get more complicated when you have to do something with the waste and pay for it. But in this simple example, you don't get anything like pour it into the sea or something. Now, there are certain limits on how much each of these 3 boxes A, B, C can process in a week. Maximum 70 tons in A and 16 B in C. And you have to pay for every ton of Gummiberry juice that you buy. There's a certain cost. And you can sell these 2 products. That's the price that you get for the product. So what is the question? The question, there's a quote in the slide, but the question is, what do you do? Okay, more precisely, how much juice should you buy? How much of this should you sell? How much of this should you sell? And how much should you pour into these 3 boxes per week? Those are the questions that you want to. That's long, and the goal, of course, is to make it much more. The question clear? You got the solution yet? I think you have because it's in the handout, but it would be cheating. So let's do the solution now. So this is a typical kind of problem. I think this is quite a common problem in manufacturing businesses. They actually are doing things like that. Of course, they're much more complicated, and you've got many more processes, and you have to work out what to do. And here you're assuming that you can just sell as much cola as you want, and as much bull as you want. But sometimes you have to assume that there's a certain amount, minimum that you have to produce, or a maximum that you can't sell more than. Things like that. But let's just do the simple situation as an example. And yeah. So, right. I've just named all the decisions that have to be made. And they were, and I'll stick to the notation that I have. So the decisions I've named them all. Okay, so there was how much I have to buy. For some reason I call it A. And this is in tons per week. The reason I call it A here is that last year I just asked the students and they said, let's call it A. So I stick to that. Okay, then we have to decide how much we're selling of the bull and the cola. So sell bull and sell cola is the amount of gummy bull. Sold, again, it's in tons per week. And then the last and then the last thing I said, we should decide how much we put into each of these boxes. Do you want any other decision variables? Do you want any other decision variables? You could have, or you don't need any more. Why not? How do you know that you don't need any more decision variables? Well, you don't sometimes. So if you're doing something more complicated, you just think you can do everything now. And then you write your constraints and you realize that you still need some more decision variables. Then you go back and add them. And this is how it works. It's not, like I said, it's not a set process that if you follow the procedure, you get it right immediately. Sometimes you just have to think, go back, fix things. Sometimes even you just produce a perfectly good LP formulation, then you solve it in Mosul, you get a solution which solves the formulation, but you can see that it's completely stupid and cannot be implemented in practice. So then you go back and that's how it works. This is why students don't like it, because students like, give me a question, the set answer, no, if I work on it, then I get the answer. But that's not what mathematicians do. Mathematicians get a question and they're stuck most of the time. Okay. Stop talking. What is the objective? The objective is to make as much money as possible, which in more precise terms is called maximized profit. Okay, profit is always, not always. Okay, because the previous example is a counter-example to what I was going to say. But in this case, profit is revenues minus cost. So your revenue is what you earn, and your cost is what you have to pay for. So in this case, what you earn is the money from cola and bull sold. So the revenue is going to be 120 times how much bull you sell plus 98 times how much cola you sell. Is that clear? It's clear now. It's going to be clear next time you do it. Okay, and the cost is, okay, so there's a cost for buying the juice, which is £12.50 per each ton. And there's also a cost of running each of the 3 boxes, which is given in the table. That's box in there. It is. So £35 for everything I put into A, and 37 per ton I put into B, and 20 per ton of what I put into C. You should be telling me this. You're too tired. Is that right? It's not going to take much longer. We only have the constraints to do, but they're important. Okay, there's this thing that if you wanted to, you could call the pipe constraint. It's probably more often called continuity constraint. And the pipe constraint okay, so what there is here is that you can't store the juice. Okay? If you're buying, well, store, you don't want to really put it to the side. You can't do it. So in fact, what the pipe constraint says is that you buy as much gummiberry juice, exactly the same amount, that you're putting into A and B. So you can't, on the one hand, can't create any gummiberry juice that you don't buy, because that's not what you're doing. And on the other hand, you don't want to buy more than what you're putting into A and B. So you don't know what to do with it, because that's this dot at the end of the pipe. Okay? So you can't dispose of it in any way. So the constraint is called juice continuity. And it says that the amount you buy is exactly equal to what leaves the pipe. And that's the amount you put into A plus the amount you put into B. Okay, any questions about this constraint? So the next time you see a problem like this, we will be able to do it. Okay, of course there are the other pipes as well. So for each of them you need a constraint. So there's this intermediate thickened juice, right? Okay, that's this pipe. And we want, on the one side of the equal sign, we want the amount that's entering the pipe. And on the other, we want the amount that's leaving the pipe. So the amount that's leaving the pipe, that's XC, because you don't do anything else. You can't do anything else with the intermediate thickened juice. then pour it into C. Okay, that's what this pipe does. There's only one outgoing. Oh, there's an arrow missing. What is entering the pipe? The answer is in the table here. So how do you get intermediate thickened juice? You get it from box A, 0.3 tons per ton of input into A, and 0.4 tons of grain per 1 ton of input into B. So XA is how much you put into A. 0.3 times XA is how much you get out of A. So for every ton you get 0.3. XB is how much you put into B, and 0.4 XB is how much you get out of B. That's the total of the intermediate thickened juice you get, and this is. And then finally there are two more pipes. So there's a gummy polar continuity constraint. I'm tired. Didn't think that not. So for the cola you get 0.2 times X B plus. Making mistakes in my head. Is that right? I'm going to fall asleep very soon. Huh? You think you have a right to be tired, but I also have a right to be tired. I created all this from 8 in the morning, and I finished at about 3 and then went to drink. So I can also be tired. Any more constraints? Pardon? Limits. That is indeed key. There are the limits. So what are the limits? There are the limits on XA, XB, and XC. So XA can't be more than 70, XB can't be more than 60, and XC can't be more than 30. But of course, they can't be less than 0. And also, All the remaining variables can't be less than 0. This one. Well, this time you don't need them. In this case, if you don't state these 3 constraints, then nothing bad can happen because A is the sum of XA and XB, which are non-negative, and SC is the sum of these, which are non-negative, and so on. So if you miss these out, that's okay. Other than that, I don't think there's anything. Can anybody see any other constraint that I've forgotten? Any questions? You think that's enough for today? Okay, well then have a good week. What you're going to do in the lab, what we're going to do in the labs is, you see, I'll show you, or Philip will show you how to run Express, which solves modal things. Okay, and then that's it. So enjoy the rest of your week.